I want you to do something for me right now. Take a deep breath through your nose.
Okay, I am doing it.
So, statistically speaking, there is a very good chance that you just inhaled past a colony of living creatures. They're microscopic, they are clinging to the lining of your throat or your nasal passage, and they're essentially just paying rent inside your body.
That is a vivid and slightly unsettling way to start our deep dive today.
I mean, it's the reality. For most of us, these bacteria are just like silent roommates. They hang out, they feed, they reproduce, but they don't break the furniture. We call that carriage. You carry them, but you aren't actually sick.
Right, it's a peaceful coexistence.
Until it isn't. Because sometimes, for reasons that have basically kept scientists up at night for a century, that silent roommate just snaps. It goes from being a passive hitchhiker to a violent home invader. It crosses the barrier into your blood, your lungs, or even your brain.
And that transition, that sudden flip from harmless carriage to invasive disease, is arguably one of the most critical mechanisms in all of infectious disease biology.
Which is exactly what we are getting into today. Welcome to the Deep Dive. I'm your host, and today we are unpacking that specific biological switch. We are looking at a bacterium called pneumococcus, or Streptococcus pneumonia, if we're being formal about it.
Glad to be here. And we should probably note right up front that pneumococcus is a massive global health priority. I mean, it is a leading cause of pneumonia and meningitis worldwide.
Yeah, it's a heavy hitter. And we aren't just looking at, a single lab report for this. The source material for today is a massive global meta-analysis published on March 14th, 2022.
It's an incredible piece of work.
It really is. These researchers combed through tons of data, pulling together 80 different publications from 18 countries to essentially answer one big question. How dangerous is this bug, really?
Right. And specifically, they wanted to calculate a metric called the case-carrier ratio.
The CCR.
Yeah.
Which I know sounds like a really boring statistic at first.
It does sound a bit dry.
It does. But as we are going to find out, it is actually a window into a really startling inequality. Because what this study found is that the danger of the bacteria doesn't just depend on its DNA, it depends on your zip code.
Exactly. It fundamentally challenges the assumption that biology works the exact same way everywhere in the world.
So let's get right into it. We have our source material. We have our mission. But before we get to the global inequality part, we have to understand the tool they used. What exactly is a case-carrier ratio?
To understand the ratio, you really have to understand those two states of existence we just touched on. First, you have prevalence. That is the carriage.
The silent roommate.
Exactly. If I walk into a kindergarten classroom and swab everyone's nose, a certain percentage of those kids will have the bacteria. They're totally fine. They're running around playing. They are carriers.
Okay, got it.
Then you have incidence. That is the invasive pneumococcal disease, or IPD. That's the kid who actually ends up in the hospital with a high fever and a severe blood infection.
So the roommate has pulled a knife.
Essentially, yes. Now, the case-carrier ratio is simply a math problem. You take the number of disease cases, the attacks, and you divide it by the number of carriers.
Okay, I need to visualize this. I was actually thinking about this earlier.
Yeah.
And tell me if this works. It's kind of like traffic safety, isn't it?
Go on, let's hear it.
So imagine carriage is just the number of cars on the road. You have 1,000 cars driving on a highway. That's your prevalence.
Okay, yeah.
And disease is a car crash.
Right.
If you just count the crashes, you know how messy the road is today. But if you calculate the ratio, like how many crashes happen for every 1,000 cars, you actually learn something fundamental about the risk itself. You learn the probability that the act of driving leads to crashing.
That is a perfect analogy. And here's exactly why that specific number is so incredibly valuable to us in epidemiology. It is very easy to count cars.
Because of the nose swabs.
Exactly.
Uh-huh.
I can send a team to a school with some cotton swabs and give you the carriage rate in a single afternoon.
But it's hard to count the crashes.
It's incredibly hard, especially in low-resource settings. To catch every single case of invasive disease, you need highly functional hospitals, you need blood culture labs, you need around-the-clock surveillance, and a lot of places in the world just do not have that infrastructure.
So the data we get is just full of holes.
Full of holes. But, and here's the magic of the CCR, if we know the ratio, if we know the crash rate, we can cheat a little bit. We can just count the cars, apply that ratio, and mathematically predict how many crashes are happening, even if our hospitals can't see them all.
Oh, I see. It's a predictive model. You're using the easy data to solve for the hard data.
Precisely. We use these transmission models to figure out if a vaccine program is working or to predict the severity of the next outbreak. But here is the massive snag we've run into. For decades, we have been calculating that ratio using data almost exclusively from places like the UK, the US, and Finland.
Wait, so we calculated the crash rate on the German Autobahn and just blindly assumed it applied to a dirt road in a rural village?
That is the crux of the entire problem, and that is exactly why this new meta-analysis is such a big deal. They finally tried to build a global map that actually reflects the reality of the whole world.
So let's talk about that map. They covered 18 countries, which, I mean, that sounds pretty global on the surface.
It is definitely better than usual,
Yeah.
but when you look closer at the methodology, the bias is still staring right back at you. Out of those 18 countries, 13 were upper middle or high income countries.
So mostly Europe and North America again.
Yes. And only 5 were low income or lower middle income countries, places like the Gambia, Kenya, and South Africa.
Which really just shows how incredibly hard it is to get this paired data. You need a study that measures both the basic nose swabs and the severe hospital cases in the exact same population at the exact same time.
It's a logistical nightmare. That's why we have so few solid data points from the places that actually carry the highest burden of the disease. But the data they did manage to get from those 5 low-income countries was completely revealing.
And they weren't just looking at pneumococcus as a single monolith, right? Because I know these bugs wear different coats.
They do. We call them serotypes. The bacteria wraps itself in a sort of sugar capsule, a coat, and there are roughly 100 known types of these coats. This study calculated the danger rating for over 70 of them.
So bringing back to the traffic analogy, we aren't just counting cars broadly. We're distinguishing between a safely driven Volvo and a speeding Ferrari.
Exactly. Some serotypes are totally like the Volvo. Very common, very safe, incredibly low crash rate. Others are the Ferrari with no brakes. They might be rare, but they are highly invasive.
Okay, so here is where the findings of the study get really interesting. They have the car models and they have the crash rates. Now they compare the wealthy countries to the poorer countries. Let's look at the pre-vaccine era first. This is before the big global vaccine campaign started shifting the landscape.
Right, and they specifically focus on children under 5, because that is the most vulnerable demographic by far.
So take the non-vaccine serotypes. These are the wild strains floating around. In the wealthy countries, what was their danger rating?
The case carrier ratio in the wealthy countries was 103.
Okay, 103. Now, what was it in the low-income countries?
For the exact same types of bacteria, the CCR was 177.
Wow, that is huge. That is not a rounding error at all. That's almost double.
It is highly statistically significant, yes.
But wait a minute. Help me reconcile this. If I have serotype X in my nose, and I am sitting in London, I have a certain risk level. If I get on a plane, fly to Malawi, and I still have serotype X in my nose, why does my risk of invasive disease double? The bacteria hasn't changed. Its DNA is exactly the same.
The bacteria is exactly the same, but the battleground is totally different.
The road conditions.
Exactly. In epidemiology, we talk a lot about host factors. Think about it. In a low-income setting, that young child is significantly more likely to be malnourished. They might be constantly exposed to indoor smoke from cooking fires, which actively damages the lung lining. They might have heavy co-infections. Maybe their little body is trying to fight off malaria or a severe viral infection at the exact same time.
So the defensive wall is just lower.
The mucosal barrier, that physical wall that keeps the roommate trapped in the nose and out of the bloodstream, is severely compromised. So even a relatively weak bacteria finds it very easy to just slip through and invade.
So the invasiveness isn't actually just a property of the bug. It is a relationship between the bug and the poverty it happens to be living in.
Precisely. And think about what that means for all our predictive models. If we just blindly use that 103 number from the wealthy countries to plan a health intervention in a poor country,
We are going to vastly underestimate how many kids are actually going to get sick.
and we will completely underprepare our hospitals.
Yeah.
This study proves that invasiveness is contextual. You simply cannot copy-paste biology across economic lines.
Okay, that is a really heavy finding, but honestly, it makes intuitive sense. Poverty creates physical vulnerability. But then I got to the part of the paper that totally confused me. I've started calling it the vaccine plot twist.
Ah, yes, the post-PCV era.
Right. So we introduced the pneumococcal conjugate vaccine, the PCV. It explicitly targets the worst offenders, the Ferraris, and it works. Those specific serotypes essentially disappear from the population.
They do, But nature absolutely abhors a vacuum. When you wipe out the dominant aggressive bacteria, other serotypes immediately move in to take their parking spots in the nose. We call this serotype replacement.
The understudies come onto the stage.
Perfect way to put it. Now, in high-income countries, let's look at what actually happened to the overall danger rating. The bad guys left, the new guys came in, and the CCR dropped from 103 all the way down to 26.
Which is an incredible success story. So the new bacteria that moved in were basically wimps.
Essentially, yes. In wealthy nations, the vaccine cleared out the killers, and the bacteria that replaced them were truly harmless passengers. The overall invasiveness of the entire bacterial population just collapsed.
Okay, so that is the absolute dream scenario for public health. Now, what happened in the low-income countries?
In the low-income settings, the CCR for these replacement serotypes stayed at 173.
Wait, it didn't move. It was 177 before the vaccine and 173 after.
It was barely a blip. The systemic danger level remained almost exactly the same.
I really want to make sure I understand this because it seems incredibly unfair. In rich countries, the vaccine killed the bad bugs, and nice bugs moved in. In poor countries, the vaccine killed the bad bugs, and equally bad bugs moved in to take their place.
That is exactly what the data shows. The danger gap between the rich and the poor didn't close at all. It actually widened.
Why? Why would the biology react so completely differently to the exact same vaccine?
That is the multi-million-dollar question right there. The authors of the study have a few working hypotheses, and it mostly comes down to bacterial competition.
Like turf wars in the nose.
Think about the environment again. In a high-income setting where you have good nutrition, excellent hygiene, maybe much lower transmission rates, the bodily environment is somewhat forgiving. It allows weak, polite bacteria to thrive and hold territory once the bullies are finally gone.
Okay, so the nice guys can actually win if the conditions are good.
But in a low-income setting, the environment is incredibly harsh. You have high rates of broad antibiotic use, high transmission rates because of sheer overcrowding, and chronically compromised immune systems. It is a very rough neighborhood.
So the wimpy bacteria just can't survive there anyway.
Exactly. The environment acts like a brutal filter. It aggressively selects for toughness, it selects for aggression. So when you knock out the top dogs with a targeted vaccine, the only things tough enough to step up and replace them are other aggressive strains.
That is incredibly depressing, actually. It almost sounds like the environment itself is fighting back against the vaccine.
It is a really stark reminder that a medical intervention, like a simple shot in the arm, doesn't exist in a vacuum. You cannot just vaccinate your way out of a problem if you don't also address the underlying ecosystem of poverty that naturally selects for these dangerous bugs in the first place.
And it means our predictive models were just dead wrong again. If we honestly thought the vaccine would lower the crash rate in sub-Saharan Africa the exact same way it did in Europe, we were dreaming.
We were essentially using the wrong map, and this study is finally giving us the right coordinates to navigate with.
Let's shift gears a little bit because we've been talking a lot about geography and income, but the study also looked closely at who is carrying these bugs. We know kids under 5 are the main target, but did they find any groups that were surprisingly safe?
They did, and it's a really fascinating bit of human biology. They found that the case carrier ratio was lowest in the 5 to 14-year-old age group.
The elementary and middle school years.
Yeah, it seems to be the absolute sweet spot of immune resilience.
Why is that? Do we know?
Well, by the time you are 5 years old, your immune system has seen a lot of action. It has learned how to handle these specific bacteria. But you aren't yet dealing with the gradual wearing down of the immune system that happens as we age into adulthood.
So a 10-year-old might walk around with a nose absolutely full of pneumococcus. They're a heavy carrier, but their body is just incredible at keeping it locked in the nose and completely out of the blood.
Right, which is exactly why you don't see nearly as much invasive disease in that specific age group, even though their carriage rates are astronomically high.
What about other risk factors? We touched on co-infection earlier. I assume HIV status played a really big role in these numbers.
It did, and this study strongly confirmed what we have long suspected clinically. The CCRs were significantly higher in HIV-positive individuals. Again, it comes down to the wall. If the host's defense is compromised by a virus, the passenger easily becomes an invader.
Did they look at gender at all? Because I feel like in every deep dive we do lately, we find out that major diseases present totally differently in men and women.
Interestingly, in this specific case, the bacteria is a totally equal opportunity offender. They found absolutely no significant difference in CCRs by sex. Boys and girls face the exact same level of risk.
You know, there was one specific line in the conclusion of this study that really stuck with me. For a paper that crunched millions of data points from 80 publications in 18 countries, the final tone was surprisingly humble.
Substantial variation remains unexplained.
Yes, that is exactly the line.
It's just true. Even when you rigorously account for age, for regional income, for HIV status, for vaccination history, there's still just a lot of noise in the data. We still do not fully understand why Kid A carries the bug safely for 8 months and Kid B with the exact same profile gets severe meningitis overnight.
Biology's just messy.
It is deeply messy. Maybe it's subtle genetics. Maybe it's the specific microbiome, like what other microscopic bugs are living in the nose that day. Maybe it's local air pollution levels on that specific Tuesday. We simply don't know yet.
But, and I think this is the key takeaway for the public health scientists listening, even with all that noise, these new numbers are the best tool we have right now.
The authors confidently call them the most representative estimates of invasiveness currently available.
So if I am a modeler sitting in an office in Geneva or Atlanta, and I am trying to predict the next 10 years of pneumococcal disease spread.
You desperately need to plug these new numbers into your spreadsheet. You cannot use the old rich country numbers anymore. You have to use the ratios that actually match the economic reality of the specific region you are working in.
Tailored epidemiology.
Exactly. It allows us to finally stop guessing and start actually predicting reality.
So let's zoom out for a second to wrap this up. What does this all mean for you, the listener, who might not be a professional epidemiologist? We started this whole conversation talking about a biological hitchhiker in your nose, and we somehow ended up talking about the global economy.
I think it fundamentally shifts our basic perspective on what disease actually is. We tend to be very reductionist in medicine. We think bacteria equals bad, antibiotic equals good.
It's just a straight fight, us versus the germs.
But this comprehensive study shows that invasiveness, the very measure of how objectively dangerous a germ is completely fluid. It changes. A bug is really only as bad as the context it currently lives in.
Context changes biology. That is the phrase that just keeps coming back to me as we talk.
It is the absolute truth. Income level isn't just a totally abstract number in a bank account. It is a literal biological variable. It physically changes the structural integrity of your mucous membranes. It changes the competitive landscape of the bacteria in your throat.
Which means if we want to truly lower the danger rating in low-income countries, if we genuinely want to close that massive gap, we might not just need a slightly better vaccine.
A better vaccine certainly helps. But to actually close that gap, to organically get that CCR down from 173 to a safe 26 like we saw in the wealthy world, we might need better sanitation, better childhood nutrition, clean indoor air.
We basically need to pave the road so the car doesn't crash in the first place.
Precisely. The purely medical solution can only go so far without an equally strong social solution.
It's a really powerful reminder that public health is, well, it is public. It intrinsically connects everything together.
It really, really does.
So here is a final thought to leave you with today. We so often talk about the war on disease like we are fighting an alien invasion. But if the actual invasiveness of a bacteria depends so heavily on your zip code, are we really fighting a biological enemy? Or are we mostly just fighting the biological consequences of our own systemic inequality?
That is the ultimate question we have to answer.
Definitely something for you to chew on this week. Thank you for joining us on this deep dive. We will see you next time.